Hey, hello everyone. My name is Jiten Balaparthi. I'm a consultant and then corporate trainer. I deliver trainings in Go, Rust, and Clojure programming languages. I also deliver trainings in Docker, Kubernetes, Kafka, and then latest DevOps related tools, microservice architecture. These are the things I do. Okay, this session is about the dynamic dispatch. In the previous session, I explained about the static dispatch. Now I'm going to explain about the dynamic dispatch. So what is dynamic dispatch? Dynamic dispatch means it's a runtime polymorphism. Okay, it's a enable it enable the polymorphism at runtime. Okay, what is runtime polymorphism? We already discussed about the static dispatch. Now you might have understand the static dispatch. Otherwise, you can go and then have a look at the video that I already uploaded about the static dispatch. This is about the dynamic dispatch. Dynamic dispatch means the polymorphism, the method, which method to call is decided at runtime, not by the compiler, but at the runtime. How dynamic dispatch is achieved using in Rust. There is a lot of content is there in this particular presentation about the dynamic dispatch with respect to C++, how it happens in C++, how it happens in uh, Rust, how it happens in Rust. However, I would like to give you a clear information about this. Dynamic dispatch happens through trait objects because traits are only the way we can achieve polymorphism in Rust. Rust doesn't have inheritance. Rust doesn't have hierarchy of types like in Java, C Sharp, C++, whatever. We cannot implement multi-level or multiple inheritance on types, but we can implement certain things using traits. Traits are analogous to interfaces or protocols in other programming languages. How how do you say that certain trait object is using dynamic dispatch, not the static dispatch? If the trait object is if the trait object is using dynamic dispatch, definitely it doesn't use IMPL keyword to implement to pass the trait object. Second thing, it doesn't use generics as the parameters whenever it is implementing a dynamic dispatch. When there is a dynamic dispatch, trait objects use underscore dyn rate. There is a special method underscore not sorry not an ampersand dyn which is a reference to the trait object, or there is a box dyn pointer. Box, you know that box is a pointer. Box dyn trait, that means you are creating a pointer of smart pointer of a dynamic trait object. That also, if any one of these you see in your code, that means it is doing a dynamic dispatch. So what happens whenever it uses a dynamic dispatch? Whenever Rust uses a dynamic dispatch, like in C++, it uses a concept called vtables. What is a vtable? V, a vtable is nothing but a virtual table. That means there is at runtime, it creates some table at runtime. Rust creates some table in the memory, which we call it as a V table, virtual table. Generally in C++, in whichever the type you see something like a virtual keyword is seen in your class, uh, immediately it will go and create a V table. In Rust, whenever it sees, it means, I mean to say, the compiler sees that a and ampersand dyn, okay, or box dyn, it creates a dynamic dispatch. It creates a V table. So let's come to the concept. Actually, there is a lot of stuff, uh, how vtables are created, and stuff like that. And there is a difference between vtable in C++ and then vtable in Rust. C++ vtables are very uh, the implementation is quite big because C++ has got inheritance concept, multiple or multi-level. So whenever the base class has a method which is a virtual method, definitely a vtable is created for each and every derived class. As far as I remember, each and every derived class. That means there are multiple vtables are created. But in Rust, actually, uh, whenever you use ampersand dyn or the box pointer of dyn, it creates a vtable for that particular object. Two times you are calling a trait object, two vtables are created. Okay. So what does that particular vtable contains? Vtable contains two things. Vtable contains number one, vtable contains, if you clearly look at this particular diagram, vtable contains this particular area. If you have a look at it, vtable contains this. Both of them are dynamic dispatch. If you any you can look at anything. First one is it contains the data. Data is nothing but the data of the actual type, the object of the actual type. That means the type could be metadata of that particular type. That means what type it is, what methods are there for that particular type. Type information, okay, metadata of the type. First thing, a pointer to the type, a pointer to the type. T means the type. The second thing is vtable, which is also pointer. This is also pointer. This is also pointer. This particular pointer contains a destructor, which destructor is used for deallocation. Generally in Rust, destructors are used by drop traits. Drop implementation is there for every time it is going to destruct an object from the memory, which is called deallocating something from the memory. And there are size and alignment. There are two other variables, size and alignment, and these are the method pointers. These are the pointers of the actual methods. These are the pointers of the methods of the type that is it is going to invoke. So this dynamic trait contains two things. One is the actual data of the type, either rect or data or metadata of the type, rect or square. And the second thing is vtable contains the destructor and the pointers of the methods. This is what the vtable contains. For every implementation, for every time you go and create a dynamic dispatch, every time you go and call the method or a uh, ampersand of dy1 or the box of dy1, it is going to create one vtable. That means 10 times you call, 10 vtables are created with respect to data. Okay. This particular information I have taken from this particular website. Mr. Michael F. Bryan, he has written this particular content. Thank you. I'm thanking him. I have taken from this. And the second thing is this is also created by Google engineers. Raf has created this particular diagram. This content I have added, but this particular diagram is written by Raf. Thank you very much, Raf. Credit goes to both of them. Okay, let's go and implement dynamic dispatch. What I do is I just copy the code. I don't want to recreate the code. Already it's there for the static dispatch. Cargo new dynamic dispatch, and let me add that particular project. Add folders. There's a dynamic dispatch. I go here. I copy pasted the code here. What does this code contains? This code contains a trait, area and perimeter, and a implementation of rectangle, implementing trait methods, implementation of square, implementing trait methods. That means we have two types, rectangle and square. Those two types has implemented trait methods. Come here. This is a static dispatch implementation. I go and then call here. So I can either call dyn or box. I called dyn of the type, and here definitely it will expect references. It expects references because we are passing a reference over here. So the implementation is same. Instead of IMPL, I use dyn. In fact, I can also use dyn, and then I think I can remove this. Sorry, I'm very sorry for that. I can also use IMPL. I can also use IMPL box. I have to use again. It is going to be dynamic dispatch. I can use dyn, percent of dyn. Then this is a dynamic dispatch. So how do you know this is a dynamic dispatch? Is not a static dispatch. So dynamic dispatch creates vtables. That is the implementation happens by your compiler at runtime, because runtime will add vtables. Why runtime adds vtables? The reason is pointers can be obtained only at runtime. So the pointers are obtained at runtime. A vtable is created and then pointers are attached to that particular vtable. You know that vtable has two things: data and then the vtable pointer and data. Data is the actual object, and the vtable is contains the destructor. That means when it has to deallocate from the memory, and also the size of the pointer size, basically pointer size, and then there is the pointers of the methods that a trait has got. These two methods here in our case. So this is the R1 rectangle, this is the S1 square. So I call this method, this is a function that we implement, calling the type, printing area of that particular type, printing area of this particular type. Any type that implements this particular I shape can be called here, can be passed here. So this is one vtable was created because R1 is an instance of course rect, but also passed as an instance of dyn I shape, right? So every time you pass one instance, it gonna create a vtable. Every time you pass instance, it gonna create a vtable. Here also S1, similarly S1 is an instance of square, and also it's not, but also, and also passed as an instance of dy and I shape. That means two times we are passing an instance of trait. So two vtables are created. Let me go, oh, sorry, let me go here, uh, dynamic dispatch, cargo run. You see that these two methods are running. Two methods are run. The two methods are there. Okay. There is a target, and then there is a dynamic dispatch is created. Two methods are run. Okay, cool. So how do I know that its vtables are created? You can use Rust compiler has got emit. What it gonna emit? LLVM IR is emitted. What on what you want to see the LLVM IR? LLVM IR intermediate representation of LLVM. You can see by calling the actual RS. Sorry, Rust spelling is wrong. Rust spelling is wrong. It has created a LLVM IR code. So you can see there is this vtable is created, but if you see more than that, if you see there are more than one vtable, so you can see vtable 1 and vtable 2, because two times you have called that particular object, we got two vtables, vtable 1 and vtable 2. Whereas in the static dispatch, if you see it, there is only one vtable. See that there is only two implementations are there. There is only one vtable, only vtable 0. There are only two. But for dynamic dispatch, there are, right, two vtables. Let's say I go and create another instance of R1, a rectangle. I call it as R2, and then once again I will call this method R2. It's R2, sorry, R2, and then I will run the code. I will create this one, R2. I call R2. Okay. See that there are 10 implementations of vtable. There are 10 implementations of vtable. Earlier we have got only 6 implementations of vtable. That means these vtables are called multiple times. These vtables are called multiple times as the method arguments. There is a object of R1. The vtables are called multiple times because there are two types of objects, rect and square, and then the methods of those objects are called attached somewhere at the runtime. So we have got 10. You can see 10 times they are all called. So this way we can understand that yeah, we have created a vtable. Let's say I have another one. What I do is I simply call cuboid, and I have got height as well. Okay, I created into self.h. I'm sorry, I don't know. I'm self.h, just putting in there. I don't know whether this formula is correct or not, but cuboid is there. Then I'm going to create, let's say, C1, and I put a height as well. Height, which is called cuboid. I put height as well, and then I call cuboid as well. Okay, you are going to print four things ultimately. You have got one, two, three, four. Two rectangles, one square, and then one cuboid. So when you go and create the ML representation of that and see vtable, you see that whenever a new type is created, a new vtable is created. So the number of types that are created, a new vtable representation is created. There are three types, three vtables are there. There are two types, but three objects. There is a one more object of the same type. The way how vtables work is adjusting the pointers. Vtables are very efficient. It will not go and create vtable for each and every object, but each and every type that is created for the dynamic object, that is for the object of that particular trait. Cool. Okay, the code will be uploaded. I mean, it will be given in the description. This is one thing, and the other thing is